So, hey everyone, today we'll be talking about enabling read affinity for RBD workloads. We'll go through how we can use it to have faster reads in a Ceph cluster deployed by Rook uh, or external clusters too. So, I'm Rakshith. I've been working with Ceph CSI and Rook for about 2.5 years right now. I was with Red Hat, now we've transitioned into IBM. So here's my GitHub and LinkedIn links. So coming to the agenda, we'll first go through the crush algorithm and the crush maps. Just a little bit of a summary, a brief intro, then OSD topology. This will be how we'll discuss how Rook implements this. Then OSD topology and crush location, how it interconnects. Then we'll see how client writes goes about, then the client reads, then some merits and demerits, and finally how to enable this for internal and external cluster. So let's get started. So we have the crush algorithm. So yeah, it's very famous because it is the core of how Ceph runs. So yeah, so coming to the starting point, RBD, Rados block device. So we first have the objects being created whenever a client writes data. This object has an object ID. So crush algorithm applies a hash on it to get the PG ID. PG is the placement group. It basically maps onto a couple of OSDs, and one of them is the primary OSD. So whenever a client writes the object, it is first returned to the primary OSD, and the primary OSD then replicates it to the secondary OSD. This is how the write happens. So the OSDs are decided based on the crush map so that it adheres to the failure zones. We have each replica copy of the data in each failure zone. Then let's go ahead. So we got the cluster algorithm and overview of crush maps. So this is the specific things. Like we have 3 zones, we have 2 OSDs in each. There's a primary OSD and secondary OSD spread across each zone, you can see. This is the same process. Client writes the data. We have object ID. From it, we derive the PG ID, and from the PG ID, we get a couple of OSDs. One of them is the primary, and a write directly goes to the primary. And it's replicated from the OSD to the other OSDs. After it is replicated, only we'll get an ACK, and that ACK is given to the client. So, okay, to OSD topology. Uh, so in Kubernetes, we already have topology. It's basically like segregation of nodes into various racks, data centers, or zones, or regions. So we need to implement segregate OSD so that we know we can have a failure domain where if one zone or one region fails, we have copies of data in the other two. So I'm talking about like with the replication factor of 3. So the entire slides will have a replication factor of 3 by default. So here Rook takes few of these already existing topology labels and few more and converts this. So first part you have the label name, then slash is the key value. The value is mapped with the key value is mapped with the value, which is basically like region east or west. These are labels on the node. So Rook extracts this and considers this as the crush location of each OSD. So whenever OSD deployment is spawned, it is spawned with these crush location values. So next, so here we can see the node topology labels being hostname as A, zone 1, region east. So this translates into cluster location of node A, host 1, and region east for OSDA. So let's go into the right part. So that is Squidward. It is for a cartoon character from SpongeBob SquarePants. We got the Quincy, Seth Quincy release from him. Squidward Quincy Tentacles is his name. So I'm going to call app/client as Quincy from now on. So this is a basic setup of 3 nodes. We have host A, host B, and host C. And at the moment, Quincy is on host A. So we got an object and we got a PG1. We've derived it to the top left. So then he writes data into OSD1. This replicates it to the secondary OSD here and here. But what if Quincy is on host C? It has to write all the way here to OSD1, but still it replicates to the other two ones. This is for the reads. Let's go into that was for the writes. This is for the reads. So if Quincy is on host J, it can directly read from the primary OSD. So the reads also come from the primary OSD by default in Ceph or in Kubernetes, wherever you read it from. Yeah, so what if this is well and good? We have it in the same node and the reads are pretty fast. What if it's on C? If the Quincy is on C, it has to read all the way from host J, OSD1. But we do still have data on OSD3, which is nearest, but we still have to go all the way here to get the data. So if it's considered as 3 node, it's pretty simple, but this can also apply to zones, regions too. So the latency will be very, very high. So is there any way we can solve it? Okay. So we already we can read from here, but this client doesn't actually know its location, but we know the crush map. So here we have a solution for it. So Ceph CSI is the one that actually maps the client with, it maps the image for the client on the node. So it has access to the node labels, which Rook uses in the first place to distribute OSDs. So it supplies this information as crush location and enables read from replica to be set as localized. So now we know the client location. We already have the crush map and all the required details. So we can read directly from the secondary OSD instead of going to the primary OSD. So this is the main cartoon character, SpongeBob SquarePants. Yeah, so this explains the whole process. So Ceph CSI, while it's mounting RBD image on the node, it just reads the labels, extracts the required crush location and passes it as kernel mount options. It's currently being implemented for KRBD mount options. And these, the info for like which labels this FCSI should read comes from Rook when Rook deploys it, or user can set it as like his own custom values. So yeah, we've achieved read affinity from the local OSD, which is like nearest wherever it is, instead of going all the way to the primary. So here we have some merits. Enabling read affinity, as we have already seen, it gives significant faster reads and increases IOPS and lowers latencies. This is especially significant when you have cross AZ traffic. Uh, in the cloud, especially, the costs are very prohibitive. So it's better to have local traffic rather than cross AZ traffic. This does that. Then Kubernetes cluster. Okay, so if you have, what if you have an external Ceph cluster? And it's kind of a stretch cluster, or it's like spread out, and your Kubernetes cluster is located near one region. You need to it's better to read data from the nearest OSD rather than going from the furthest nodes. So this also helps do that in case of external clusters. Then finally, we have a Metro disaster recovery setup. So Metro disaster recovery is like, consider you have two racks and you have a stretch cluster in between them. And you have two Kubernetes cluster, one in each rack. So if one cluster fails, the app has to automatically fail over to the other one. So here, I'm talking about two racks, it's nearby, but you can consider even data centers. So we have to read from the nearest data center Ceph cluster instead of going to the further one. So with this read affinity, we can do that also. The Kubernetes cluster in, let's say, a primary cluster in data center A will always read from the OSDs in the data center A itself and will not go to the another B. And yeah, if it fails over, there the data center location will be set as B, so the reads will go to that Ceph cluster. So demerits. So like if we have multiple clients spread over AZs and they go for the same data piece, it usually went to the primary OSD. That is, a single OSD would serve the same data for all the clients. But now multiple OSDs, all the primary and secondary OSDs are serving data for reads. So there will be increase in CPU and memory usages. because like yeah, it depends on the IO patterns and stuff, but this can happen. That's one of the demerits, but yeah, there is excellent trade-off between like performance and increased memory and CPU usage. So how do we enable it? For Rook to apply deployed internal clusters is just one step. You just set this CSI enable read affinity to true in the config map and you're done. So you will get read affinity for any newly mounted RBD pods. So if you have workloads already running RBD pods, you just have to restart them after this config map comes into effect. For external cluster, so there are chances that your topology labels may like collide with the ones already in existence for Kubernetes clusters. So you may have to like use new labels on the nodes, like external cluster.topology.rook.io/zone east. So this separates it from the regular Kubernetes labels. And yeah, if SFCSI will then extract this the crush location from this, just the last two parts are important, zone east. Then yeah, the same command which we used in the last slide to enable read affinity. And you're done. You have a read affinity for internal and external cluster. Okay, these are some references, ceph.io. Then we have Rook GitHub link and ceph-csi driver link. You can just scan it for the slides and the links. Thanks. Do we have any questions?
For the internal mode, I guess nodes also need to add the label. Hello. I guess it's audible. So internal mode you show.
Hey.
Hello. So for the internal mode also, you said we don't need the node labels, but I guess we have to apply it before.
So for in internal mode, Rook already spreads the OSDs according to the node topology labels. So the OSD crush map itself comes from the existing node labels.
Okay, so you are saying they are already applied
Yes.
to the node?
Yeah.
Okay, thanks.
It's already applied. Okay. Do we have any other questions? Can you pass the mic?
Have you tested about the effect of using read affinity in an environment where you have like a 50% read-write or 70% write and 30% read? How is the contention handled when one pod using the affinity is just like doing more writes and another pod on another host has a majority of reads? Any cross impact between the two pods?
I think there has not been like such testing because this feature came into existence like a few months ago.
Yeah, I know.
Yeah, so yeah, from the preliminary
Just in case you had the chance to do it.
yeah, from the preliminary testing, we've observed like good improvement in latencies and performances. And another effect was the increase in memory and CPU usages of OSDs.
Yeah. The other benefit is the cross AZ traffic, as we
Yes.
discussed earlier, that
Yeah.
it will be a huge benefit
Yeah.
for most customers, definitely.
Yeah, thanks. I think he had a question.
Add a comment. Was it on? So, push the button. All right, yeah. So I think to answer your question, I mean, maybe it's already obvious. The more writes you have, the more contention you'll have because the writes don't get this advantage, just the read. So you're just looking for numbers or.
Yeah, it's more about the log handling because one pod is going to do writes using, the mapping that it does on one node. Although the writes are going to be replicated, but the primary, the affinity is just used for the read.
Yes, only for the read. Yeah. So it's like after we get the write ACK only after the data has been replicated. So we can use read affinity there. Okay.
So show again what do they have to? So they have to put the labels on the nodes for the read
for the
affinity.
external cluster.
Yeah. So to enable it, it's the labels on the nodes, and
just enable it.
and enable that crush location labels. But we have. Why isn't this turning on? Anyway, don't we have the external topology labels by default?
I mean, like Rook, like Kubernetes clusters already have their own kind of labels, right? Yeah, there is default labels,
Right.
but they don't have to like necessarily match with the crush maps of the external cluster.
Right.
Yeah.
So if it's
It,
okay, if it's not matching the external cluster.
Yeah.
For a local cluster, it's fine. This is
Mm.
for external cluster.
Yeah.
Okay, got it.
I think there was another question.
I have a question about read operation. Actually, I'm not familiar with this operation. It seems like client like RBD.
Yeah, it is for RBD workload.
Same OS node, right?
Hmm?
The Quincy is like a
Quincy is a client or an application.
normally client driver is working in the worker node and OS is different node, right?
Yeah, this is like an example of a 3-node cluster. You can consider it for zones as well. Like you have multiple zones, you have masters and worker nodes in all of them. So the reads will go in the same zone itself.
Yeah.
Yeah, that will still have the same effect. That answer your question?
Okay. Yeah. Okay.
Ah, okay.
Complement the question, if his application was running on a different worker node, but as long as they're in the same zone, because the label would be shared, your application running on one worker node would go to the worker node where the OSD is running if you were having separate nodes to run the Rook cluster. So it would still be a benefit anyway.
Yeah, like it crawls through the, we have a lot of cross locations. Like it just crawls through the ones with, like first is host. It tries to find the nearest OSD on the same host. It doesn't find it. Then the region, then the zone, then the data center. So in this way, it finds the nearest OSD which has the data, whether it's primary or secondary, then the read is given from that. Okay, do we have any other questions?
So, do we know why it is not enabled for self-office? We have the same crush algorithm for both, right? RBD and self.
Okay, the question is like why it is not enabled for CFFS. So yeah, I spoke to the CFFS developer. So the crush location, there is no way to currently pass it to the kernel's FFS client. It can be done, it seems, easily, but it's not currently available. So if we pass the crush location to the same underlying layers, it can be done. The reads can go to the nearest OSDs. Do we have any other questions? So the question was like, how are you finding the nearest location? So we basically have a crush map. That a crush map is like where the OSD is located. It basically crawls through the crush map to find the nearest OSD. Like if there is a OSD with this piece of data in the same host, same zone, or same region. So like if we go, yeah, so if we go here, that is the crush location of the OSD. We have that. Like if we add up all the crush location of all the OSDs, we get a crush map. So we just crawl through it and find the nearest one. Yes. Do we have?
Identifying the nearest OSD is at the Ceph layer, right? That's not the CSI driver.
Yes, we just pass the, yeah, we just pass the client to crush location and it does the mapping and identifying the nearest one. Okay, do we have any other questions? Okay.
I do have a question. Do you have a plan for write affinity? You don't have to answer that.
Yeah, it's fine. Yeah, it'll be a great Ceph tracker issue if Ceph developers actually accept it. Okay, thanks guys.